Hi, this is Sam Ziss from Dr. Uselin's Thermodynamics class. I'm going to be working through some concepts from Chapter 2 by applying them to this problem that I wrote. We'll start by reading the problem statement. It says, a dam collects power from a flowing river using a turbine. The water flows at a rate of 180 cubic meters per second. If the water falls from a height of 120 meters to a final height of 10 meters, calculate the efficiency of the turbine if it is known that its power output is 150 megawatts. Take the density of water to be 1,000 kilograms per cubic meter. Our ultimate goal here is to calculate the efficiency of the turbine. I'll start by writing down the pieces of information that were given to us. The statement says that the water flows at a rate of 180 cubic meters per second. We will call that the rate of change of the volume, 180 cubic meters per second. We were given that it begins at a height of 120 meters and falls to a height of 10 meters. So we will say that the change in our height is 120 meters minus 10 meters, getting us 110 meters. The power output was 150 megawatts, and the density of the water was 1,000 kilograms per cubic meter. Our goal is to find the efficiency. Efficiency is calculated by dividing power output by power input. We were given the power output was 150 megawatts. So in order to calculate our efficiency, we will need to find the power input. Power input, or the rate of change of the energy, can be found by multiplying the rate of change of the mass by the energy. So that's going to be what we go after. We can find the rate of change of the mass by multiplying the rate of change of the volume by the density of the water. We have both of those pieces, so we're going to multiply 180 cubic meters per second by the given density of 1,000 kilograms per meter cubed. This is going to give us a value of 180,000 kilograms per second. The other piece that we need is the energy. We can find that with the help of Bernoulli's equation. We know that the change in pressure divided by the density plus the kinetic energy plus gravity times the change in elevation will get us this value. We don't need all of these values. We were not told anything about the pressure, and we were not told anything about a change in the velocity. So we can get this energy just by multiplying gravity, which we will take to be 9.81 meters per second squared, times that change in the elevation, which we calculated to be 110 meters. This calculation is going to get us 1,079.1 meters squared per second squared. And I'm going to make a little change to this value. I'm going to multiply this by 1 kilojoule per kilogram divided by 1,000 meters squared per second squared. Giving a little background on that conversion, there are 1,000 meters squared per second squared in 1 kilojoule per kilogram. The reason we're making this conversion will become clear in the next line. Once we do make this conversion, meters squared per second squared are going to cancel out, leaving us with 1.0791 kilojoules per kilograms. We are now ready to go calculate the power input. Again, we will multiply that rate of change of the mass, which we found to be 180,000 kilograms per second, by that energy of 1.0791 kilojoules per kilogram. And here's where you can see why we made that conversion. Our kilograms are going to cancel. When we make the calculation, this is going to get us 194,239 kilojoules per second. We are talking about units of power here, so I'm just going to go ahead and rename this kilowatts. A watt is 1 joule per second, so a kilowatt is 1 kilojoule per second. And again, that's why this conversion back here was so useful. And really, you kind of just get more experience with knowing when to make these conversions as you do more of these practice problems. Again, looking back at our goal, because we are not yet done here, we're supposed to find the efficiency. So we will go divide our power input that we just found underneath our power output, which was given as 150 megawatts. In order to get similar units here, I'm going to multiply that 194,239 by 1 megawatt over 1,000 kilowatts, getting us our final power input as about 194.2 megawatts. So for the final step of this problem, we can go get our efficiency. Again, efficiency is power output given to us as 150 megawatts divided by our power input, which we found to be 194.2 megawatts. This calculation is going to get us a decimal value of 0.772. I'll convert it to a percentage by multiplying it by 100, giving us a final answer of 77.2% efficiency for this turbine. Thank you very much for watching.